This first podcast is a podcast on an introduction to acids and bases. So most of this information in this first acid-base podcast will be rather general. So let's start with some basic definitions of acids and bases. Now there are three ways to define an acid and a base. The first method is the Arrhenius method, or the Arrhenius model of defining an acid and a base, and this is the one that we are most familiar with. And in regular chemistry, this was probably the way that acids and bases were defined. An acid produces hydrogen ion in solution, and a base produces hydroxide ion in aqueous solution. This also happens to be the most narrow definition, so it's the most useful definition probably for us, and it's also the most narrow definition of an acid or a base. So an acid in the Arrhenius model would be something like HCl. A base in the Arrhenius model would be something like NaOH, so that OH in there that can be produced in solution. The second method of defining acids and bases is the Bronsted-Lowry method, or the Bronsted-Lowry model. Now this one is a little bit more general, and for us in AP chemistry, this is really the definition you want to keep in your mind. Acids are proton donors, which essentially means they're putting H+ into solution. So that part of the definition goes along with the Arrhenius model very well. The second definition, bases are proton acceptors. This is a little different, a little broader. What this does then is it allows us to include negatively charged polyatomic ions as bases according to the Bronsted-Lowry model. So something like PO4 with a -3 charge would be considered a base because it can pick up an H+, which is essentially a proton. So this does allow us a slightly broader definition. Now the last model or method is the Lewis acid model or method. We're not going to spend a whole lot of time on this, but it's defined according to electron pairs. So acids are electron pair acceptors, bases are electron pair donors. So again, the one you're familiar with here on the screen is Arrhenius. We want you to try to start thinking in terms of Bronsted-Lowry. So H+ acceptor, H+ donor. And then the third definition, which is probably the least useful for us, is the Lewis acid model or definition. Now, when an acid is put into solution, our generic formula for an acid is HA, it will donate a proton into solution, and you'll get an H+, and then you'll get an A-. The A- is called the conjugate base, so it's like the negative part of the acid that comes off into solution. So if you reverse this reaction, that A- would be the thing picking up the H+. So it is called the conjugate base. Now for weak acids, we are going to write what is called the acid dissociation expression. So you can see that here clearly on the screen, and it's again products over reactants, just like all the rest of our equilibrium constants. And we do this for weak acids. Now strong acids would dissociate completely, so there's no point in writing a Ka, because keep in mind equilibrium constants are for those systems where there's an equilibrium set up. So for strong acids we would not need this. Now, many textbooks and teachers will include water in this equation. So they would have H2O on the left, and then on the right side, rather than writing H+, the H+ attached to water would form what we call the hydronium ion, H3O+. So in place of the H+, we could write H3O+. Those two things are interchangeable and basically mean the same thing. Okay, so you're going to see both of those. Now, dissociation of strong acids. As I said before, strong acids are assumed to dissociate completely or near completely. So before dissociation, you see in the red we have HA. When that strong acid goes into solution, we're going to have an equal molar solution of H+ and A-, and everything dissociates. So the Ka for a strong acid dissociation would be huge, very large. so large we don't even write it. And we would say that reaction favors the products. So in other words, it goes totally forward, totally dissociates, and we don't worry too much about an equilibrium. So dissociation constants for strong acids, as you can see, they're not even really calculated. We just say very large for all of them. So these are your typical 6 strong acids. So you need to kind of memorize these if you haven't already. HClO4 we probably use the least. HI, HBr, and then those 3 there, HCl, HNO3, and H2SO4, we see those quite commonly. So notice there is a table for these acid dissociation constants, these Kas, but we don't really use them because these dissociate near 100%. Now, weak acids, on the other hand, notice before dissociation in the red, you see HA, and there's a lot of it. Notice after dissociation, you still see a lot of HA, and then you see a little bit of H plus formed and a little bit of A minus. So these things, these 3 species then, are in equilibrium with each other. So weak acids tend then to have a small Ka, small being less than 1, positive but less than 1, and we say that these weak acids favor the reactants, not the product. So you're going to have a lot of the molecule still left in solution and not so much of the H plus and A minus. That's why weak acids tend not to be as acidic, because they're not spitting out a whole bunch of H plus into solution, whereas the strong acids basically give up all their H pluses. And pH is a measure of those H pluses that are in solution. So here's a table of some common weak acids and their Kas, and as you can see, they range all the way from iodic, which would be the strongest of the weak acids on this table, all the way down to hydrocyanic, which would be the weakest. So the larger the Ka, the stronger the weak acid. The smaller the Ka, the weaker the acid is. So large Ka means you have a stronger weak acid. Small Ka means you have a weaker weak acid. And we're going to use these Kas in future podcasts for calculations of pH.